Welcome back everybody to another exclusive JLAM Bio video. Today we are going to be focusing on the periodic table and ionization energy. Now, please keep in mind that I've gotten about 2 hours of sleep, so I may sound goofy, make really odd jokes, and just giggle for no reason. I'm kidding, of course. Well, not really. Probably about the giggling, but just about everything else might actually happen in this video. So stay tuned, because it's going to be funny, and it's going to be about the periodic table and ionization energy. Hopefully by the end of this video you will be able to understand the organization of the periodic table, or organization, depending on how you look at these kind of things. You should also be able to analyze properties of the periodic table and explain ionization energy and how it plays a role in how charges are formed. So we're going to dive a little bit into the periodic table, not super deep today. You just need to make sure that you understand the different groups, understand metals, nonmetals, metalloids, those types of things. We have a lot of different vocab terms for this. We're going to talk about Mendeleev and his development of the periodic table. We'll talk about groups, periods, different types of elements, so main group elements, transition metals, lanthanides, actinides, noble gases, alkali metals, alkali earth metals, halogens, metals, nonmetals, metalloids, ions, anions, cations, and ionization energy. A lot of vocab for this unit, so make sure you're up for it. I know I am. Let's rock and roll. So in the mid-1800s, Dmitri Mendeleev attempted to arrange the elements based on chemical properties. Now, again, this was the mid-1800s, so he didn't have a whole lot of really strong information, but he focused on how they reacted in certain circumstances. So, for example, lithium, sodium, and potassium. He noticed that when they were placed in water that they produced hydrogen gas when they reacted with the water. He also noticed that they were good conductors and formed bases as well. He noticed similar trends with magnesium, beryllium, and calcium. So he basically looked at the different elements that were available and reacted them, looked at boiling point, melting point, looked at density, and as a result of that, he was actually able to organize a really crude version of the periodic table. If you look on the right-hand side here, you've got your listing of all of the different elements that were known at the time. And you notice how a lot of them follow trends. Now, some of them don't. So, for example, if you look at copper, silver, and gold, based on how they reacted, they're actually very, very similar to group 1. Because I don't know if you remember, but copper, silver, and gold all have a +1 charge when they are in their ion form, very similar to lithium, sodium, potassium, rubidium, cesium, and so on. And you notice the same for several of the other metals, like if you look at +2, zinc is thrown in there. So a lot of this has to do with how they reacted. But also notice that there are some gaps in the periodic table as well. This is really interesting, is that based on that information, he was able to determine where elements that haven't even been discovered yet would fit on the periodic table. So it's really interesting how he managed to organize this based on chemical properties. And then based on spaces that were left behind, he was able to determine that there were certain elements that just simply had not been discovered yet. One of the key things that he noticed is that every 8th element had similar properties. Now, if you think about back to what we've talked about previously about the octet rule in Chemistry 1, this kind of makes sense. Every 8th element, if you take out the transition metals, appears in the same group. And so they would have similar properties. This is known as the law of Mendeleev. And as we discussed before, he was even able to predict the presence of unknown elements. Only 70 were known at the time, as opposed to 118 that are currently known today. So when we take a look at the modern periodic table, it is very simple, yet actually portrays a lot of information about all of the different chemicals and elements that are listed on it. Now, when we describe the rows on the periodic table, we describe those as periods, or we also describe them as energy levels when we talk about things like electron configuration. But periods are what we're going to focus on. That is the rationale of why it is called the periodic table. And the columns on the periodic table are known as groups. Now, columns of elements will have similar properties. You may remember this from Chem 1, that everything in the same group has a similar charge and therefore is going to react a similar way with similar compounds to produce similar products. Magnesium is going to react with oxygen in a very similar way that calcium will, or strontium will, or barium will. Fluorine, chlorine, bromine, and iodine are all going to react in a similar way as well. So keep in mind that a lot of these groups will have similar properties associated with them. Now, when we divide these groups, we focus into really 3 special areas. We have our main group elements, which include groups 1 and 2. We skip all the transition metals in the middle, and then focus on groups 13 through 18. So you're looking at boron group all the way through your noble gases. The transition metals are the metals that are in between, and it makes sense. They're called transition metals because they transition from groups 1 and 2 to groups 13 through 18. Now you notice that down at the very bottom of the periodic table we have a group of elements that are called lanthanides and actinides. These are actually kind of groups that go to the right as opposed to groups that go up and down. They're called this because elements 57 and 89 are lanthanum and actinium, and they're just simply named after that. They're also called rare earth metals. Reason being is that you don't typically see these elements very often. You don't typically use them very much in chemistry class, so they are somewhat rare. When we look at specific groups on the periodic table, the first group are known as the alkali metals, and they're very reactive. Reason being is that they have one valence electron in their outer shell, and they're desperate to get rid of it to have a low potential energy. Very similar to alkali earth metals, group 2, which have 2 valence electrons in their outer shell. They're also quite reactive. We'll experiment with this later on. Chalcogens are what are known as group 16, which kind of comes from a term that refers to oxygen. You have your halogens in group 17 and your noble gases in group 18. So it's really important you make sure you know, at the very least, these 5 key group names on the periodic table. Now, the periodic table is also organized in a way where we can divide it into metals, nonmetals, and metalloids. If you notice on the periodic table, there is a giant stair step. That giant stair step indicates the differences between your metals and nonmetals. On the left-hand side of that stair step, you have all metals. Now, metals are shiny, they're malleable, which means that they're flexible, they're easy to bend and manipulate. They are ductile, meaning that they can easily be formed into a wire, which makes sense. You know a lot about probably copper wiring and things like that. And they're also good conductors of electricity. You probably know this as well, as metals conduct electricity very, very well. Now, to the right of the stair step in kind of that grayish color are your nonmetals. Nonmetals are dull, brittle, and very poor conductors of electricity, basically the opposite of metals. Metalloids are kind of somewhere in the middle. So if you look at that green group right there that kind of travels right along that stair step, they have chemical properties that are in between metals and nonmetals. And this creates some really interesting chemical properties. So really key thing to remember, make sure you understand your metals, your nonmetals, and your metalloids, and also understand the properties that allow them to, and make sure that you also understand the properties of these metals, nonmetals, and metalloids. The last thing I want to talk about today are ions, and the periodic table has a really good method of showing how ions are formed. Now, ions, as we talked about previously, are formed when protons do not equal electrons. Anions have a negative charge, meaning that they gain electrons, and cations have a positive charge, which means that they lose electrons. Remember that we don't change the number of protons, because if we do, we change the element. Now, ionization energy is something very important. It is the amount of energy required to remove an electron. So as we discuss further, I want you to keep that in mind and also understand that most atoms want to have 8 electrons in their outermost shell. That is when they have the lowest potential energy and as a result are the most stable. So as I mentioned before, consider the octet rule from previous chemistry classes. Where would you find the lowest ionization energy? Well, low ionization energy means it's really easy to remove an electron. And those with just 1 electron in their outer shell are going to be able to have that removed very easily. Because once that is removed, then they have 8 in their outer shell. The electrons removed, so for example from sodium, then the electrons become 10, which means that they have 8 in their outer shell. So that means that it is very, very stable. The highest ionization energy are things that are going to already be stable because they don't want to remove an electron. So the example of that would be things like your noble gases, helium, neon, argon. They already have 8 electrons in their outer shell, and it's going to require a lot more energy to remove an electron than it would for other elements that, if they remove an electron, would then have 8 in their outer shell. Typically, a good way to think about this is that metals want to lose electrons and nonmetals want to gain electrons. Now, this is not always the case, but when we discuss ionic bonding a little bit later on, you'll kind of see how this works. But basically, everything to the left of the stair step wants to lose electrons, and everything to the right of the stair step typically wants to gain them. It's a pretty good rule of thumb. But again, it's a rule of thumb, so it's not always the case. Hey, that's all I got for this video today, guys. So hopefully you're able to meet those student learning objectives that we talked about previously. Make sure you know your groups. Make sure you understand how the periodic table is organized. Know your properties of metals, nonmetals, metalloids, and how ionization energy plays a role in number of electrons and things like that. Appreciate your time, guys. If you have any questions, make sure you let me know. JLand Bio signing out. Have a great day, guys, and we will talk to you later. Bye-bye.